Welcome back. In the last couple of videos, we really hammered the ideas of what it means for events to be independent, and we reviewed how to calculate OR probabilities, since those tend to trip people up. So, starting in this video, we're going to begin talking about probability distributions, what they are, how to calculate things with them. If you have taken my one semester probability and statistics course, you might be a little familiar with the example we're going to start with, but even if you haven't, you're not behind because we're going to do it now. So, if you took the class, what's important is not that you've seen this example before, but I want you to be able to tie it into the realm of things we've been learning about probability. I don't want it to exist as some isolated thing that you know. I want you to be able to tie it in to what we've been talking about. So let's get going. Let's say you're at a carnival. Yay! Remember when carnivals existed? You could pay $5 to draw from a standard deck of cards, right? And this is what happens. If you happen to draw the ace of hearts, so this is not a heart, this is the ace of hearts, you win $100. Not bad, you only paid $5, and if you draw the ace of hearts, you can win $100. If you draw any other ace, then you win $10. If you draw any other heart that's not the ace of hearts, you win $5, which is essentially your money back. And if you draw any other card, you lose that $5 that you paid. So, if you're not familiar, a deck of cards has 52 cards in it. There are 4 different suits: clubs, hearts, diamonds, and spades. There are 13 of each of those. So 52 divided by 4 is 13, 13 of each suit. And within each suit, there are the 2, 3, 4, 5, 6, 7, 8, 9, and 10, Jack, Queen, King, and Ace. Right? So, you should be able to figure out how likely it is to get any of these results. And we will be doing that. But I want to know if you would play this game. Is there a right or wrong answer to that? No. This question is subjective. It's up to you. And furthermore, I don't really care. It doesn't matter whether you would play this game or not. I suppose some people would, some people wouldn't. Whatever. The interesting question about this game is, should you play the game? And what I mean by that is it statistically advantageous to you to play this game? Well, what the heck does that mean? Well, we should be able to find out if you pay $5 and you were to play this game over and 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 over. Would you end up making money by playing this game, or would you be losing money? Obviously, if you only play the game once, the odds are stacked against you. Most of the cards in the deck are not hearts or aces. But, I mean, this payout's pretty big, and it does happen once in a while. So, is that enough to counteract how much you lose? Well, let's find out. Let's write out all the different possibilities in terms of how much you can win and how likely that is to happen. So we're going to make a probability distribution table here. And we're going to have the different amounts of winnings and the probability that you receive any of those winnings. So if you took my one semester course, I've used this example, but we talked about the profit, how much you make, but that makes some calculations a little more difficult. So we'll just talk straight up how much you win. What is the highest amount of money you can win by playing this game once? You can win $100. And yes, I know that if you pay $5, you've actually won $95, but we will actually be talking about this number because it doesn't really matter either way. So you can win $100. And how likely is that to happen? Well, There are 52 cards in a standard deck, and the Ace of Hearts is one of those cards. So the probability that you draw exactly the Ace of Hearts is going to be 1 out of 52. Not super likely. That's a little less than 2% of the time. Right? Next highest amount of winnings, $10. What's the probability of getting that? Well, any other ace. That's going to be the ace of diamonds, spades, or clubs. There are 3 of those cards out of the 52. You can also win $5. And that's if you get any other heart. And we established there are 13 hearts total in the deck. Any other heart than the ace, so we're taking 1 out of that 13. That gives you 12 out of 52. And it's possible for you to win $0. And how likely is that? Well, when you draw from the deck and you play this game once, either this happens, this happens, this happens, or this happens. So I suppose you could count up all the cards that wind up in you losing, but the easiest way might be to use the complement rule here. This is going to be equal to 52 over 52 minus all of these. So these add up to 16. 52 minus 16 is 36 out of 52. And now you understand why we don't reduce these. That would have been a lot harder if we did. So this is our probability distribution table. It specifies all the possible outcomes of the process and the probability of getting each of those outcomes. It's the distribution of the probabilities. In general, the numerical outcomes of a random process are the values of what we call a random variable. So, in order for something to be a random variable, it has to be the outcome of a random process, and it has to be outcomes that are numeric. As long as you meet both of those criteria, you have a random variable. So, drawing cards from a deck is a prototypical random process. And the outcomes, in terms of this particular example, are how much money you win. So, what is the random variable in this example? It is the amount of money that you win. I'm not necessarily sure that you would have a question on an AP test or anything like that that asked you what the random variable was for a specific process, but it could happen, and it's important for you to know because you're going to need to know what the variable is in order to construct this table accurately. So, in terms of random variables, they have their own notation. So we normally denote a random variable as x. A capital X. And we denote its individual values, which would be each of these things, as x sub I. My kitty was being annoying, so here you go. This is Bella. Hi, Bella. Hi, Bella. Okay, let's put the cat away so we can continue working with this example. Bye. Bye, kitty. Where were we? Oh, right. Probabilities of random variables. So if we denote the random variable as x, and each of the values it takes on is x sub I, whatever that is. So the first value would be x1, x2, x3, so on and so forth. Then what we might be interested in is the probability that the random variable is equal to a particular value. And that would be denoted as the probability that x is equal to x, whatever. Okay, so we can now recreate this table using the proper notation for random variables. Now, I know in this class I really hammer home the point of making sure that you include things in the context of the variables that you're interested in. And at first glance, it looks like from this table to this one, all we've done is take the context out. But I don't want you to be surprised if you see a probability distribution table with this notation. I just want you to know that this, and this could also just be x, represents the values of the random variable, and this represents the probability that any of those individual values occurs. You may also see this table with some kind of variable definition. So x is still equal to the winnings here. All right, so a few definitions now that we're introducing random variables. They can be defined as either discrete or continuous random variables. And first, a discrete random variable is one that can only take on a countable number of values, each of which is associated with a probability. Now, this is a discrete random variable, and that's because it can only take on 4 different values, and by this I mean the winnings. There are only 4 different values that the winnings can take on, and each one has a probability associated with it. Not all variables are discrete. Some are continuous, and those would be ones where we might use the normal distribution, for example. Things like heights, weights, stuff like that, right? Things that can take on any value in an interval. Okay, so if you're dealing with continuous random variables, you're not going to have a table like this because there are infinitely many different values that the random variable can take on. You're only going to see tables like this for discrete random variables because there are only a certain number of possible outcomes. Things like the number of, or the amount of winnings when you're playing a game, rolling a die, flipping a coin. Like, these are all discrete random variables that only have so many different outcomes. But I do want you to keep in mind some variables are continuous. We're only going to be talking about discrete random variables in this probability unit for now. Also, each value's probability, when we're talking about a discrete random variable, must follow this. The probability that the random variable is equal to a particular value, all of those probabilities have to be between 0 and 1. So they must also follow the rules of probability. And for the probability distribution to be considered valid, if you add up all of the probabilities, they must add up to 1. So I have seen, it's a very common question on AP tests, that they might give you a table like this, or maybe they'll just give you the setup, and you have to answer, is this probability distribution valid? It's not, does it appear to make sense? It's asking for this. Do the probabilities add to 1, and are each of the probabilities between 0 and 1? So is our probability distribution valid under these rules? Well, again, there are only 2 things it has to follow. 1, each value's probability has to be between 0 and 1. And all of these are. Do they add up to 1? Well, yes. In fact, the way that we calculated this probability is by taking 1 minus the rest. So by definition, it has to all equal 1. But I wouldn't put it past the College Board to try and give you a probability distribution that is not valid because one of these rules is not met. All right, so let's link this example back to what we've been talking about in the past. Now, instead of having a two-way table or a Venn diagram or a tree diagram, we're going to be able to answer questions about probabilities from our table. It's kind of like a two-way table, except there's just one variable now. Only winnings. That's the only variable we have here. So what is the probability that x is, I don't want to know the probability that x is equal to 5. I want greater than or equal to 5. Right? So to answer this question, you need to know several things. First of all, what does the P stand for? And some people don't remember. It's probability. Right? X represents the variable, which is winnings. So this is asking what is the probability that the amount of winnings is at least 5. So that would be anything greater than or equal to 5. And there are at least 2 ways of calculating this probability. You could take all the different outcomes for winnings that are at least 5, which is going to be 100, 10, and 5. Take all those probabilities and add them together. So you could write it out this way. Oops, I disappeared. The probability that x is equal to 100 plus the probability that x is 10 plus the probability that x is 5. Now we can just substitute in those probabilities and we get 16 over 52. 16 over 52. That's one way to do it. Can you think of another way? We could use the complement rule. Now that we have our complete table, the probability that x is greater than or equal to 5 instead of adding up all 3 of these probabilities, which is easy enough, but let's say we didn't want to, we could just take 1 minus this probability. So that's 1 minus the probability that x is 0. So either way we get 16 over 52, and if you have the probability distribution table, calculating any kind of probability should be fairly straightforward. Probably easier than when you have 2 variables at the same time. And just one more note, the word discrete in terms of probability distributions or random variables, it's a homophone. There is another word in English, discrete, that's like, oh, don't worry, I'll keep your secret. I'll be discreet about it. That one is spelled this way. D-I-S-C-R-E-E-T. That's not the word that we're using. This is D-I-S-C-R-E-T-E. Just a small point, but one that's important nonetheless. Let's do one more example here. I apologize. I asked a question a little earlier down there. Should you play this game? And we don't quite yet have the tools to answer that question. But we will. Maybe you have an idea. Should you play that game or not? I wonder how you would even determine that. Oh well. Let's go to our next example here. I promise we'll get the tools to figure that out later. All right, here's the distribution of grades from a section of Calc 1 at IU Bloomington in a recent semester. I was amazed. I was just looking for things I could use as an example. I was like, how about grades? I wonder if they post those online. They do. Now, they don't post individual students' grades, but at IU Bloomington, I could go to Calc 1, and then I could see by professor the distribution of grades. So this is for one of the Calc 1 professors. Different professors would have different probability distributions. I thought that was immensely interesting. Anyway, first question, is this probability distribution valid? Do you remember the 2 things you need for a probability distribution to be valid? Each of the probabilities needs to be between 0 and 1. They all are. And they need to add up to 1. And I'll leave you to do that as an exercise, but yes, they do add up to 1. So, I'm being lazy. I'm just saying yes. For you, you would need to actually show why. Maybe I should even say explain why or why not here. It's because each probability for every value of the random variable is between 0 and 1, and all of the probabilities sum to 1. So to interpret what's going on here, this is using like the GPA scale. So A is a 4, B is a 3, C is a 2, D is a 1, F is a 0. So when you see the values of the variable here, those represent the grades in the course. So X is equal to the GPA score, essentially. Why didn't I just say A, B, C, D, F here? Well, I wanted it to be numeric. I wanted it to be a discrete random variable that was numeric so that maybe eventually we could calculate the average GPA score of a student in this class, which is something that we'll be able to do in a future video. But for right now, the only other question I've got here is this one. What is the probability of a randomly selected Calc 1 student at IU Bloomington receiving a C or lower in that class? So a C or lower. So that would be C is 2. C or lower would be any of these results. So answering this question is as simple as saying, well, we want the probability that X is less than or equal to 2. And we could get that by taking the probability that X is 2, X is 1, and the probability that X is 0, and just adding all those together. Why do we add them together? Because a student can only get a C or a D or an F. And so we're saying here the probability that X is less than or equal to 2. Okay, I actually skipped this step. My apologies. Let me write down all the steps here, just so it is clear where it's coming from. This is most directly translated to this. X equals 2 or X equals 1 or X equals 0. And from what we've determined already with the basic rules of probability, or means add. Now you may remember when we talked about the general addition rule of probability, this doesn't necessarily turn into this unless the events are disjoint. Luckily for us, a student can only get one grade at a time. They can either get a C, a D, or an F. If these events were not disjoint, we would have to take this sum and subtract out any probability of getting more than one of these at the same time. But since these events are disjoint, you can't get more than one grade at the same time, the ORs do break into just the sum of the individual probabilities. So we take these and add them together. 0.279 plus 0.163 plus 0.047. And that is 0.489. Which is terrific, but chances are this wouldn't be the question that you would be asked. It would be this question and then maybe calculate this probability and interpret what it represents in context or something like that. So how do you interpret this number? This is a very important skill in this class. Calculate your answers and then interpret them. Well, you could leave it as a decimal, but more easily interpreted are percentages. So this as a percentage, it'd be 48.9%. And when it comes to interpreting answers like this, I don't like trying to make up this sentence on my own. I like stealing from the problem because the language they use is probably acceptable to them. So I would maybe say 48.9% of Calc 1 students at IU Bloomington receive a C or lower. There you go. If they ask, what's the probability of a Calc 1 student at IUB receiving a C or lower? Well, 48.9% of Calc 1 students at IUB receive a C or lower. There's no way to be misinterpreted there if you use the language that they're already providing. If you try and come up with it on your own, you might actually say something that's not correct. And that would be a shame if you got this answer, but your interpretation was off. So that's just a good skill. Take the language they give you and use that to interpret your answers. So in this video, you have now been introduced to probability distributions, which we generally write in these tables. And you now are a little more clear about what random variables are. And specifically, we're talking about discrete ones right now. We'll get to talking about how to deal with continuous random variables. That's going to be a little later. We're going to need a whole different toolbox to calculate probabilities of those. But if you have a variable that only has certain values that it can be, like 4 different amounts of winnings or 5 different grades in a course, then providing the probabilities for each of those outcomes separately and then answering problems such as this should come fairly naturally, I would think. We're going to have to do something completely different for continuous variables, but we'll get to that later. So that's it for now. I hope that you're enjoying our unit on probability. We will continue on in the next video, and we'll see you there.